You won't be pressed for time when you're taking the exam. I'll put some of it for you to do at home. There will be a dinner review session this Thursday. There will be a Sable lunch on game theory this Friday. We will have a prospective student for Williams. I think he's only a junior right now, so it's going to be a while before he applies. Okay, so today the topic is directional derivatives. We've already seen some directional derivatives in this class, but today we're going to see more of them. And we're going to talk a little bit about applications of directional derivatives. So one of the big things always whenever you take a class is why. One of the reasons you take a class like multivariable calculus is you want to solve problems. You want to optimize. You want to find what's the best values. So in economics, this is a huge issue. And so this is going to lead into Friday's lecture on Lagrange multipliers. That's one of my favorite parts of the course. It's a nice way to apply all the stuff we're doing. It's also theoretically nice. So it's a really good mix of theory and practice. Today, however, I want to just get some of the preliminaries we're going to need for Lagrange multipliers. And this is going to force us to revisit some of the concepts we've already seen. And we're also going to see a lot of the stuff we've done from Chapter 11 coming into play. We seem to be having the class shifting backwards a little bit. It's got more space to work with today. Nice. OK, so the first thing is we've seen the definition of derivative. So anything that's important has multiple notations. We have df, we have grad f, we have upside down triangle f, df, dx1 through df, dxn. Right? So this is the definition of the derivative. And we talked about what it means for a function to be differentiable. So if all the partial derivatives exist and are continuous, then the function is differentiable. If not, then we have to worry about using the tangent plane approximation and show that the tangent plane does a really good job. For this class, almost always we are going to have functions whose partial derivatives exist and are continuous. So when we say a function is differentiable in this class, essentially that means the partial derivatives exist and are continuous. So what we want to do now is we want to talk about how to take the derivative of a function in a direction. Now, unfortunately, that direction does not have to be a unit vector. And this causes some issues in some of the formulas later on. And so I'll show you the issues that happen when you don't use unit vectors. If at all possible, use unit vectors. And so the book will say we will take the directional derivative along v, when v might not be a unit vector, or in the direction of v, which will then force v to be a unit direction, a unit vector. So whenever you take directional derivatives, if you have a choice, choose unit vectors. It's going to make the calculations a lot nicer. So here, I'm going to define a function. Define a of t to be f of x plus tv, where f is going to be some function from Rn to R. X is a point in Rn. V is v1 through vn is a vector. So I'm forming a new function. It's a great function to be formed. People love it all over the world. Okay? I hope that clapping shows up in the video. So what am I doing? I have some point. Here's my origin. Here's my point x over here. Here's my direction v. What object is x plus tv? So what kind of object geometrically is x plus tv? Is it a sphere? Is it a parabola? What's x plus tv? How am I moving? I'm moving along what? I'm moving along a line. So this is where we're starting to use all the stuff from Chapter 11. X is my base point, and I'm moving in the direction of v. So when t equals 0, I'm at x. When t equals 1, I'm at x plus v. When t is at minus 1, I'm at x minus v. So I want to figure out how this function changes. Okay? So the definition of the directional derivative of f at x along v is the limit as h goes to 0 of f of x plus hv minus f of x all over h. One of the nice things about teaching the class twice is you have the option of presenting things slightly differently. So I'm presenting things in a slightly different order than I did at 10 o'clock. I'm going to be looking at your faces and trying to see if this makes any difference at all. Why is this a reasonable thing to do? Well, if you think back to Calc 1, how do we find derivatives? We define derivatives through limits. The definition of a derivative fundamentally involves a limit. So if I'm talking about a directional derivative, I should have a limit coming in part of the definition. How many of you enjoy using the definition of the derivative to take derivatives? All right, if you really feel that way, but if embarrassed to speak up now, you can see me privately. We'll take a few derivatives. Nobody really likes to do this for nasty functions. And if I give you, a cosine of sine of the square root of x squared minus 5 and ask you to use the definition of the derivative, this would be a nightmare. This is why we spend all the time developing things like the product rule, the chain rule, so that instead of having to go back to the derivative, we can take derivatives of simple pieces and build them up. From a computational perspective, this would be a nightmare to work with to calculate directional derivatives. We want a better formula for this. And so what we're going to do now is we're going to find a computationally tractable formula. So recall, a of t is f of x plus tv. So there's two right answers. Which calculus class teaches you how to take the derivative of this function? Where would you see how to take the derivative of a function like this? So if I give you a function a of t, which calculus class do you learn how to take derivatives of functions like this? So how many variables does this depend on? Just one. So where do you learn how to take derivatives of a of t? Calc 1. Now over here, I have a chain rule. I have f of, so whenever you hear the word of, you should be thinking chain rule, x plus tv. I could write c of t as x plus tv. And this is really what we were calling g of t before. We like to use the letter c because we're typically going to be using this as a curve in space. And so we use c to talk about a curve. Now in this case, this is a very special type of curve. It's a line. So rather than using the letter c, I could actually use the letter L here for line. I'm going to use the letter c because later in the day we'll consider more general curves. So what we have is we have a of t is f of c of t. This is a Calc 1 derivative. And this is a Calc 3 derivative. This is a chain rule. So this is one of the reasons why we prove the chain rule, is to be able to handle quantities like this. So this side is very easy. We get a prime. So we get a prime of t. And now from the chain rule, we get the derivative of f at c of t times c prime of t. Now, which point do you think I care about most? So of all the values of t, which point do you think I care about the most? Well, sorry, which value of t do you think I care about most? So I have to choose a value of t. Which value of t do you think I care most about? So I'm trying to find the directional derivative of f at x along v. So which value of t do I want? Yes?
0.
I want 0, because if I take t equals 0, I'm at the point x. So what I really care about is a prime of 0, which is the derivative of f at c of 0 times c prime of 0. Let's write this out the long way using the chain rule. So C of t is x1 of t, x2 of t, dot, 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 xn of t. I claim C prime is really, really nice. If you look at it, C of t is x plus tv. So the first component is going to be x1 plus tv1, then x2 plus tv2, then x3 plus tv3. So when I take the derivatives, I'm just going to get v1, v2, v3. C prime of t is just going to be my vector v. And so what we get from the chain rule is a prime of 0 is df dx1 at the point C of 0 times dx1 dt plus df dx2 at C of 0 dx2 dt plus yada, 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 df dxn at C of 0 dxn dt. This is what the chain rule says. This over here, this is just v1. This is just v2. This is just vn. And so what we get is we get the gradient of f at the point C of 0 dotted with v, which is just the gradient of f at the point x that we care about dotted with v. And from a computational perspective, this is a much nicer formula to work with. And so it's just an application of the chain rule. And what makes it work is that it's very easy to calculate the derivative of C of t. We're just moving in a line anchored at the point x in the direction v. So C prime of 0 is just that direction v. C of 0 is just the anchor point that I care about. It's just x. And so now this is the directional derivative. So we need notation, and hopefully good notation. So notation. So we write dv of f at x is the directional derivative of f at x along v. And we'll have dvf at x is the gradient of f at x dotted with v. This is how we compute it. Best way to compute. Okay, so from a computational point of view, this is how we want to compute. And we now see here is a nice application of the gradient. The gradient is one of the key ingredients in computing directional derivatives. Now, you've already seen directional derivatives in this class. So where have you seen directional derivatives before today? You've seen them somewhere. And it's in fact on the board in some sense. I had to erase the grab candy because that's what somebody guessed at 10. Where have you seen directional derivatives? Were you looking at how a function changes in just a specific direction? Where have we done that in this class? In what sense?
Just finding directional derivative to plug into the equation. Trying to explain it.
Not quite. I mean, in what you're doing, if you say certain, in the actual calculation of the equation of the plane, we then use these specific directional derivatives. But you've seen some of these directional derivatives before. You've seen n of them. Or in three-dimensional space, you've seen 3 of them. The partial derivatives, right? If you think, what is partial f, partial x? Move just in the direction of the x-axis. Partial f, partial y, move just in the direction of the y-axis. Partial f, partial z, I feel like a cheerleader, move just straight up. You've seen n partial derivatives so far, right? These are the very special directions. And then we have this wonderful theorem that says if all these partial derivatives exist and are continuous, the function is differentiable. What's nice about these n directions is they're mutually perpendicular. Any direction can be written as a combination of these. That's why it's enough to just study the standard partial derivatives, and we can express everything in terms of them. And in fact, that's exactly what we're seeing here. We can represent a general derivative v as the gradient, which is just the standard partial derivatives dotted with v. As a nice exercise, take v to be a unit vector in the x direction, and you'll see this reduces to df dx1. Take v to be a unit vector in the x2 direction, you'll see it reduces to df dx2. So in the special cases, this formula reduces to what we've already seen. Whenever you get a new formula, you always want to test something like that. Does it reduce to what you've seen before? Yes. This reduces, so reduces to partial derivatives when v equals e1, e2, en. So it does reduce to what we've seen before. Okay, what I want to do now is I want to go to the definition of the directional derivative, which comes from the limit. And the reason we were able to get to this nice formula is, well, from Calc 1, we know how to calculate this limit. That limit is just a prime of t. So I want to just look at this formula for a moment, and I want to ask you the following question. What would happen to this limit if I double the length of v? So I'm going to keep v's direction the same, but I now want to double the length of v. So there's only three things that could happen to this limit. What are the three things that could happen? What are the possibilities? Increase, decrease, or stay the same, right? So before you do anything, try to get a sense of what are the possibilities. If I double the length of v, this is either going to increase, decrease, or stay the same. Anybody have any thoughts as to what will happen if I double the length of v? Do you think the directional derivative depends on the magnitude of v or just the direction of v? That's the question. Well, let's think. Let's replace v with 2v and see what happens. So now we have this quantity. We want to see how does this compare to what we had before. One of the things I love to do whenever I have to do algebra is either multiply by 1 or add 0. Do you think I'm going to be multiplying or adding here? So I'm going to write this. I'm going to move this 2 over here now. I'm going to put it in front of the h. So I have 2hv, but I'm only dividing by h. So does this look like a multiplication or like an addition? When you take the limit, what you change by over here has to be the same as what you're dividing by. Is that the case now? So what do I have to do to fix things? Yes? Multiply by what? By 2 over 2. So if I multiply by 2 over 2, now I have 2h and I'm dividing by 2h. Now from Calc 1, I have the correct limit. If h goes to 0, does 2h go to 0? Yeah. And so what we see is that when we multiply v by 2, it propagates. And we finally get, if it's along 2v, we get twice this. So the directional derivative has doubled if we change v. So it really does matter what the magnitude of your vector is. It's not enough to just fix the direction. You have to fix the magnitude as well. And this is why we typically use unit vectors. If I use unit vectors, everything is nice. I don't have to worry. And so henceforth, we shall always use unit vectors. Okay. So let's think about the directional derivative. I have some function, I have a point I care about, and I have infinitely many different directions I can move in. Let's say I want to figure out which way my function is changing the fastest. I want to see which direction should I move so my function is changing the fastest. So another way of looking at this is I want to find where's the directional derivative largest. Which direction should I move? So if we return, we have a of t is f of x plus tv. So if we think about what's going on, here's the origin, here's my point x, here's my vector v, and if I calculate a prime of 0, this is telling me how much I'm changing in the direction of v. So how fast changing in the direction of v. I could take another direction. Here's w, and we could let maybe b of t be f of x plus tw. And so now b prime of 0 is how fast f is changing in the direction w. So as I keep changing my vector, I'm going to be seeing how my function f is changing in those different directions. And I want to find which is the special direction to go so that my function will change as much as possible. After that, I'll want to find the direction to go so my function is decreasing as fast as possible. So any thoughts on which direction I should move to see the greatest possible change? So which direction should I go to see the greatest possible change? So to give you a sense, if you've read the material before class, this is a question you should be able to answer. You should know roughly, all these applications of the directional derivative, which way do we go to see the greatest direction, to see the greatest change. If you haven't done that, though, a really good skill is to be able to look at formulas like this and get a sense of what the answer is. So we have dv of f is going to be the gradient of f at x dotted with v. And we want to find the direction v. We want to find the way to go to make this quantity as large as possible. Most of you are not going to use most of this material ever again in your lives. Right? So why are you in Calc 105? So it's very good that you're not all storming out right now. So you're here because some of you will need to use some of these things, and you do not know ahead of time which bits you're going to need. So when you forget this stuff, it'll hopefully be easy for you to relearn it. The other thing, which is more important, is you're here to learn general problem-solving skills, general ways to attack problems. That is far more useful than the material. So in something like this, I have to sniff out which direction to choose for v. There is a natural candidate. It may not be the right answer, but there is a direction that is always present when I do the directional derivative, no matter what direction I choose for v. What direction is always present in this quantity? Yes? So good. So x is a good thing to try, but x is the point we care about, right? X has nothing to do with the function. So unfortunately, it's a good thing to try, but no matter what function I put in, I'm always evaluating things at x. So it can't be x. That's where I am. What's the one vector that's always here, no matter how I vary v? Something is always present in this formula. So where are the vectors? What vectors do you see in this expression? So whoever's answering has to speak up. So it can't be v, because v is what I'm varying. I want to find what v gives me the greatest change. What's the only direction I have? What's the only vector that's always there? I'm sorry? The gradient of f, right? This is the only vector that's left. So no matter what v you choose, The directional derivative always has the gradient of f at x. It always has this vector in it. So again, you're going to use very little of what I teach you this semester. But if you can look at problems and get a sense of how to attack them, how to search for answers, that's a useful skill. I want to figure out what v is best. Is there anything special in this problem? Is there any special direction I can latch on to? This is the gradient of f. So that tells me it's probably either really good or really bad. But the gradient of f should somehow play a role in the answer. It's the only thing that's there. And so if we look at the following. So here's my directional derivative at x. We have a way to evaluate this dot product. What formula can we use to evaluate this dot product from chapter 11? What formula do we have for the dot product of two vectors? So if I give you the dot product of p dot q, what's a nice formula for the dot product of p dot q? I'm sorry? So one is to multiply each component. Unfortunately, that's not going to lead to something that's going to be very easy for us to understand, because then I want to vary all the v's. There is a formula that involves the length of v and the length of... Well, the dot product is a number.
So it's like PQ cosine theta.
So length of p, length of q, cosine theta. This is where we're getting all the dividends from chapter 11. So this is just equal to the length of the gradient of f at x times the length of v times the cosine of the angle between the gradient of f at x and v. So this is where we're using the dot product formula from chapter 11. And so I want to see what value of v is going to make this largest. Which value v, which direction should I go to see the greatest possible change? As I change v, do I see any change in the gradient of f at x? Does that magnitude change as I vary v? Does this depend on v at all? No, this is independent of v. So independent of v. What about the length of v? Does that change as I change v? It could. I could go from v to the same direction, but twice as large. But what kind of vectors do I use for directional derivatives? I only use unit vectors. The unit vector is a vector whose length is 1. So does the length of v change as I change v? No. As v is a unit vector, length of v is always 1. So the only place where there can be any change as I vary v is in the cosine of the angle. So if I want the cosine of the angle to be as large as possible, well, cosine is always between -1 and 1. How do I get the cosine to equal 1? What must be true about the angle? It has to equal 0. So max when theta equals 0, i.e. v is in the same direction as the gradient of f at x. Yeah, there you go. They finally timed it right. Okay? This is wonderful. This is now a geometric interpretation of the gradient. The gradient tells us the direction to go for the maximum change. So geometric meaning grad f at x points in the direction of maximum change of f at x. So if I want to see which way to go to have f increase the fastest, I want to go in the direction of the gradient. Which way should I go to see f decrease the fastest? I'm sorry?
Go normal to it?
Not normal, no. So if the gradient of f I'm increasing the fastest, which way do I go to decrease the fastest? The opposite. I go in negative gradient. So Now I'm going to ask you, which direction do I go to see no change?
No.
Now I go perpendicular. So if I want to see no change, I want cosine of theta to be 90 degrees. So I want to be perpendicular to the gradient. So if you're perpendicular to the gradient, there's no change if you move a small amount. If you're in the same direction of the gradient, that's maximum change. If you're negative, that's the direction of greatest decrease. So we now have a nice geometric interpretation for the gradient. We have a nice meaning for these directional derivatives. Okay, so now it's time to do an example. Let's let f of x, y, z be x squared plus 2y squared plus 3z squared. And I'm going to take v to the beta point 3, 4, 12. Find directional derivative in the direction of a unit vector in the direction of v. So I give you a direction v. I want to find something in the same direction of v, but unit length. Unless, of course, v happens to be unit length. Is the length of v 1? No. I mean, each component is greater than 1. The length of this vector is clearly greater than 1. Anybody quickly look at this and see the length? These are cherry-picked numbers. The length of v is, what is it? 13. Yes. So it's 3 squared plus 4 squared plus 12 squared. You could calculate this directly and see it's the square root of 169. Well, I'm just going to show you how I made up these numbers. What's 3 squared plus 4 squared? 5 squared. I'm using the 3, 4, 5 triangle. So I have 5 squared plus 12 squared. This feeds into the 5, 12, 13 triangle. So this is really the square root of 13 squared is 13. So u is just v divided by 13. So I'm going to get 3/13, 4/13, 12/13. And so now the directional derivative in the direction of u at some point x is the gradient of f at x dotted with u. And so now I just have to calculate the gradient of f. All right, that's going to be 2x, 4y, 6z. And now I have to take the dot product with my unit vector u, which is 3/13, 4/13, 12/13. And so we get the directional derivative of f at u at the point x is going to just be 6x plus 16y plus 72z divided by 13. So you give me a point x, y, z, and I can tell you what the directional derivative is in the direction of u at that point. So I just need a point now. Anybody play a sporting event for Williams in the past day or two? Nobody has competed for Williams in the past day or two. All right, I will sadly use the last Red Sox game I watched with my kids. We sadly lost to the Yankees 2-5. So I will take my point to be 250. And so then I would get the directional derivative of u of f at the point 250 is just going to be 6 times 2 plus 16 times 5 plus 72 times 0 over 13. And since it was a spring training game, I don't care about the answer, and I'll just leave it like that. Right? This is how you would do directional derivatives. You would never go back to the definition of the directional derivative. You don't want to use the limit. You want to use the gradient approach. So the directional derivative at a point in a direction is just given by the gradient of f at the point dotted with the direction you care about. And always take your directions to be unit vectors. Okay, it makes the analysis a lot nicer. Okay, so this gives us an understanding of the definition of the directional derivatives. They generalize the partial derivatives. We can calculate directional derivatives. So the question now is, what are the uses of partial derivatives? Of directional derivatives. Why do we care about all these? So these are going to become some of the key ingredients when we get to Lagrange multipliers and we try to figure out, how to optimize a function. So we talked about the Farmer-Brown problem. And right now, the only way we can solve the Farmer-Brown problem, sadly, is to say, well, look, I have so many perimeters of fence, so I can replace one of my variables y in terms of x, and then I can reduce this to a Calc 1 problem. What we really want to be able to do is we want to handle constraints. And it turns out a really good way to view constraints is as a level set. And so what we're going to do now when we see these applications is we're going to revisit level sets. So I have told some of you the story of my cousin/nephew. He was in a horrible geometry class in school, and in this class, if your definition did not match word for word what was in the book, you lost full credit. As a mathematician, I complained vehemently, vigorously, whatever you want to say, to his father. And I was furious about a math class where this could happen. And I made a comment at some point in her life, I guess they taught her how to teach. How to read, not teach. And he said, no, she doesn't know how to read. She knows how to compare symbols and just see if things look exactly the same. She can't even read. She doesn't know what she's reading. I do not expect you to be able to regurgitate, nor do I want you to regurgitate word for word the definition that's in the book or my notes. This is not the point of a math class. What I want you to do is understand and internalize what these different concepts mean. You should be able to explain in words anything you're doing in this class. If not, that means you have not understood the concept fully. So for instance, level sets. There's a real rigorous mathematical definition. Don't memorize that word for word. Be able to just paraphrase and say in your own words what a level set is. So for me, I'd say, the level set of a function f of value c is all inputs that evaluate to c under f. And you make sure you put in all the correct ingredients. You've got to have your function coming in somewhere because you're talking about the level set of a function. The value c has to come in somewhere. And you just very clearly say what it is. I don't care if you use the same phrasing as I do, but you should be able to say what a level set is. So what we're going to see now is the following beautiful theorem. Let f be from Rn to R be a differentiable function. Let S be a level set of f of value k. So why have I switched? Why am I using k for the value of my level set? It's not because I made a mistake at 10 o'clock and I want consistency across sections. This is deliberate. I don't want to use the letter c. I want to save the letter c for something. What have we been using c for today? Yes? Curves. And so I'm hoping that the way you spell the word constant in German is with a k. And if so, then we've just switched to honoring the German mathematicians. But I want to keep the letter c free for curves. Let c be a, oh, it is c of t. Let c of t be a curve in the level set S such that c of 0 is my point x naught. Then the gradient of f at x naught is normal to the level set. So this is a wonderful application of the gradient of directional derivatives. It allows me to find normals to surfaces. So before proving it, let's do an example. Let's do f of x, y, z is x squared plus y squared plus z squared. So something like this. So if I take k to be negative 5, what would be the level set of this function when k equals negative 5? So what x, y, z evaluate to negative 5 under f? Nothing. So the level set is empty at negative 5. It stays empty until I reach what point? 0. And all of a sudden, at one point, now I get the origin 0, 0, 0. And now as k increases into the positive numbers, I start getting a bigger and bigger sphere. What's the radius of the sphere when the level set takes on the value k? So what will be the radius of the sphere of the level set of value k? Square root of k. Perfect. I have x squared plus y squared plus z squared is k, so the radius is square root of k. So I understand what the level sets are like. Let's calculate the gradient. The gradient of f is 2x, 2y, 2z. Or if I just pull out the 2, I just get x, y, z. This is interesting. I'm going to draw it in 2 dimensions just to make it a little bit clearer. Here's the origin. Here's some point. I'm on the sphere. And now, whoops, there's my gradient. It's in the same direction as my vector. And if you notice, it is normal to the circle or normal to the sphere. If I'm going around and around and around on the sphere or on the circle, if I want to stay on the circle, instantaneously I want to move in this direction. I want to move tangent to the circle. So this would be a good choice for my direction u. I need to move tangent to the circle. So this is tangent to the level set at the point x naught. And this is the gradient at x naught. And you can see in this case that the gradient is perpendicular to the tangent vector. Now in the sphere, of course, I would have an extra dimension. And I could take this and I could go in any of these directions. And in all of those, it would always be perpendicular to the normal. So whenever you see a theorem, you always want to try to do some special cases. If you don't like the sphere, you should try doing the equation of a plane. Look at the plane and say 2x plus 5y plus 18z equals k. And see that the gradient to that level set, so the gradient to that function, is going to be the same as the normal to the plane. So these are ways to test and see that the theory is consistent. It matches cases you know how to do. We know how to do spheres. We know how to do planes. We can use this to build up some intuition as to what's going on. All right, so let's do the proof. So we have some curves. We have c of 0 is the point x naught. C prime of 0 is going to be u, which is tangent to the level set at x naught. Right? So I have some curve. At time 0, I'm at x naught. And my instantaneous change, I'm moving in the direction u. So I'm going to consider the following function. Let's let a of t be f of c of t. And we know a of 0 is f of c of 0, which is f of x naught. And what does that equal? So what's f of x naught? So if you go back to the conditions of the theorem, I have a function f from Rn to R. S is the level set of f, so it's the set of all inputs that evaluate to k. X naught is in this level set. So what must f of x naught equal? So since I'm in the level set, it has to equal what? It has to equal k. This is the definition of being in the level set of value k. F of x naught is just equal to k. So we know what's going on when t equals 0. What about other values of t? So I tell you, c of t always stays in the level set. So what do you know about f of c of t? What must f of c of t equal? It must equal k, right? Because I'm telling you, S is the set of all inputs that evaluate to k when I apply f. C of t keeps me in the level set. Well, if the level set is all points that evaluate to k, and I stay in that level set, then I must be k. So therefore, we have a of t is f of c of t equals k. So when we calculate a prime, there's two ways to do it. One is the chain rule, and we get the gradient of f at c of t dotted with c prime of t. All right, I did one, you do the other. What's the derivative of k with respect to t? So I give you the function that's always equal to k. What's its derivative with respect to t? 0. There's no change. The function is constant. Therefore, a prime of 0 is the gradient of f at c of 0 dotted with c prime of 0, which is 0, or the gradient of f at the point x naught dotted with u equals 0. So what we've just seen is no matter what curve I take, as long as the curve stays in the tangent plane, as long as the curve stays in the level set, the gradient of f at x naught dotted with u, dotted with my tangent direction, is going to be 0. So this tells you this has to be perpendicular to every tangent to the surface. Well, the only thing that's left, if it's perpendicular to every tangent direction, it has to be normal. And so in fact, we had some foreshadowing earlier today when we looked at the gradient of f as the place where, as the direction where we had the greatest change, and we said the negative gradient was the direction to go for the greatest decrease. We also said, well, what happens if we are perpendicular to the gradient of f? All those directional derivatives are 0. Those are the directions where the function is not changing in value. And that's what we're getting over here. So the gradient of f is normal to the level set. And this is a wonderful theorem. This is going to be extremely important when we start to do the applications. So the key thing to get out of this is no matter what direction I take, as long as I stay in the level set, I have to be perpendicular to the gradient of f. And that's going to force the gradient of f to be the normal. So we have one last application. And that is tangent planes. And of course, if we're in several variables, it could be tangent hyperplanes. And so what we have is the tangent plane to the level set S of value k of a function f at a point x naught is the set of all x such that the gradient of f at x naught dotted with x minus x naught is 0. So this is a nice way to calculate tangent planes or tangent hyperplanes. So we saw that we cared about these tangent planes and hyperplanes as they allowed us to approximate a function really well. And we can do this by using the gradient. So the gradient is basically giving us, these normals that we need. And so if you think about what's going on, here's my origin as always. Here's my point x naught. I have my function somehow, and I want to calculate the tangent plane to it. And so I'm looking for all vectors x in the tangent plane such that this direction here is in the tangent plane. So that direction has to be a normal, so that direction has to be tangent to my function's surface at that point. The gradient gives me the direction of the normal. And so what I'm basically saying is, if I stay in the tangent plane, then I have to be perpendicular to the gradient of f at the point x naught. So this x naught is the point we care about, and x is in the tangent plane. So this is exactly the same formula we've had before. This is just reinterpreting that formula in terms of things we've seen today. All right, so again, a lot of material today in terms of applications of what you've seen. It's basically the dividend of Chapter 11 lecture. All right, on Friday, we will start Lagrange multipliers. If you haven't picked up your homework solution